Welcome to Empowered Learning. This is the second video in the video series discussing polar coordinates and equations. In this video, we will get into how to do polar to rectangular coordinate conversions as well as rectangular to polar coordinate conversions. So for most of you, if you're watching this video, this is the core of what you need to know in dealing with polar coordinates. And that is, how do we basically parametrically define what these coordinates are from the rectangular sort of way of looking at things and being able to convert back and forth. Now, in short, if we convert a polar coordinate into rectangular coordinates, then we're using these three equations here to help us to be able to do it. Okay. So essentially, we're saying that x is equal to r cosine theta, y is equal to r sine theta, and we are going to define our angle according to this equation here. And I have a star here because we could actually use sine a theta, cosecant theta, secant theta, or cotangent theta to be able to find that angle. The standard way of doing it is to use tangent, since we have information on the x and y coordinates in the rectangular plane. So that's why we naturally want to use tangent here to do that. The other thing that I want to bring to your attention here is that to find what theta is, we can't just blindly say that, well, theta is just going to be tangent inverse or arctan of y over x. Okay. We can't always do that, and unless you're in quadrant 1, it's really not going to make a lot of sense. And so part of the reason I say that is, let's assume that our angle theta is going to be in standard position. If it's in standard position, then that range of theta is normally going to go from 0 to, let's say, 360 degrees, if I want to refer to it that way. Okay. And I have parentheses here on 360 degrees because, of course, 360 degrees and 0 degrees is pretty much the same thing. So if we are in quadrant, let's say quadrant 4, then one of the things we have to recognize about the arctan or tangent inverse function is that any angle that is in quadrant 4 for this tangent inverse function is going to be negative. Okay. And if we are forced to have our angles be in between 0 and 360 degrees in standard form, being that that angle is positive, giving an answer for theta to be negative is not going to make sense in that case. Okay. When we have a situation like what I'm talking about here, if our angle is in quadrant 4, what we would have to do is say that our actual angle is going to be 360 minus tangent inverse of, and let me fix that right quick. So it's going to be tangent inverse of absolute value of y divided by x. And I put the absolute value there because we need to make sure that the number that results in dividing y by x is going to be positive. Okay. And so the simplest way to do that is just to make sure that you assume that both x and y are positive here when using this reference angle. Okay. Another point I want to make is, let's say we're in quadrant 2. In quadrant 2, tangent inverse doesn't even understand an angle in quadrant 2. And that is because if you look at the graph of what tangent inverse looks like, that graph basically only understands angles in between a negative pi over 2 and a positive pi over 2. Okay. And so I'll sketch that graph here quickly so that you could see what I'm talking about, just in case you may not know what that is. So in general, this is what a tangent inverse graph looks like. where the dotted line above is the horizontal asymptote y is equal to pi over 2, or let me be a little bit more formal here. Theta is equal to pi over 2. And then down here, this is the horizontal asymptote. Theta is equal to negative pi over 2. Okay. So if I had an angle that's in quadrant 2, which is an angle that's in between 90 and 180 degrees, your tangent inverse function doesn't even understand that. Okay. So again, that's why we would have to use reference angles here to be able to express an angle in quadrant 2. And if I did that, that angle in quadrant 2 would look something like, and I'm going to do this in radians, it'll be pi minus tangent inverse of absolute value of y over x. Okay. So I want to make sure that is clear before we move forward, because finding what x and y are in terms of polar coordinates is relatively easy, provided that we have the angle. But it's the angle that's the thing that's a little bit tough sometimes. Okay. Now, note that we can manipulate these equations here so that if I needed to figure out what cosine of theta was, it's just going to be x divided by r. If I needed to know what sine of theta is, it's just y divided by r. And of course, all this just comes from the basic equation of a circle centered at the origin. Okay, so that's where these parametric equations come from. All right, so now that we've discussed the basics here, we're going to go ahead and move on and try to get some examples in. All right, so just to summarize here, we know that to convert a Cartesian coordinate into a polar coordinate, of course, we're going to use this knowledge here. So basically, we're going in the other direction, whereas before we were going from polar to rectangular. Now we're going from rectangular to polar. And of course, we know that if we have some Cartesian or rectangular coordinate here, we're going to have to figure out how far that point is from the origin by taking the x coordinate and y coordinate, squaring each of them, and then taking the square root of that. And notice here that I have a plus or minus here. Most times your r is going to be something that's non-negative, but remember I told you that there are some applications where it makes sense to have a negative value of r. So I always leave that available just in case you have something that does that. So in this first example here, we're going to go ahead and skip to that. We kind of already know about this directional angle, so I'm not going to talk about that again. So in this first example here, what we want to do is convert the following polar coordinate into rectangular coordinates. Okay. So if we look at this, we already know, hey, our r is going to be 3 and our angle is going to be pi over 6. So simply put, we know x is just going to be r cosine of theta, which is going to be 3 cosine of pi over 6. And y is going to be r sine of theta, which that's going to be 3 sine of pi over 6. Now, some of you may memorize the unit circle to get these. I know personally I don't. I use right triangle trigonometry to do this. And so I'm just going to say that this is 30 degrees here. And I know that the relationship in between these sides is 1, square root of 3, and 2. And let's say if I have one where the angle is 45 degrees, then that would be 1 square root of 2. And so I use that in reference angles to be able to figure out what these things are whenever I have to evaluate things like sine and cosine. So here I know cosine of pi over 6 or cosine of 30 degrees is just going to be adjacent over hypotenuse. So this is going to be square root of 3 over 2. And so our final answer is that for the x. And for sine of 30 degrees, that's opposite over hypotenuse. It's 1/2. So that's just 3/2. So therefore, our rectangular coordinate here is just going to be x coordinate 3 square root of 3/2, y coordinate 3/2. And so as you can see, that's relatively straightforward based upon the information that was given. All right, so let's look at the second example here. So we do the same thing over again. So we know that r is 5 and our angle is a negative 7 pi over 6. So here x is going to be r cosine theta, which is 5 times cosine of a negative 7 pi over 6. And so here we know that cosine is an even function. So I could look at this as 5 cosine of 7 pi over 6. And now we note that 7 pi over 6 is actually an angle that is in quadrant 3. Okay, because we know that 7 pi over 6 is 6 pi over 6 plus another pi over 6. And of course, 6 pi over 6 is just pi. And that puts us on the negative x-axis. And then we go another pi over 6 here. So we know that this angle is in the third quadrant. And cosine is negative in the third quadrant because x values are negative in the third quadrant here. Okay, so that's what I'm saying. So we could express this as a negative 5 cosine of positive pi over 6. And so now from here, we can go back to triangles here. We know that cosine of pi over 6 or cosine of 30 degrees is just square root of 3/2. And so that will end with us basically having negative 5 times square root of 3/2 as our x coordinate. We do the same sort of thing for our y coordinate here. We know that sine is an odd function. So one way that we could look at that, and I'm going to clean this up a bit because this looks a little funny. Okay, so we know that sine is an odd function. So this could be looked at as negative 5 sine of 7 pi over 6. And then here, note again, we could use the whole reference angle thing like how we did from the 5 cosine of 7 pi over 6 to negative 5 cosine of pi over 6. And we note that sine of 7 pi over 6 is just basically a y coordinate. And as we see here, y coordinates are also negative. So we got a negative of sine of pi over 6. And of course, that negative times a negative gives us a positive. So we're right back being positive again. And then, of course, sine of pi over 6 is just going to be 1/2 because we know that's opposite over adjacent. So here we just got 5/2. And that will be it. So for this answer, we know that this will just end up being the point negative 5 times square root of 3/2 and 5/2. And one of the things I do want you to notice is that this particular point is actually in quadrant 2. Okay. And so we could have looked here and said, all right, well, where is the angle negative 7 pi over 6. If I had done that, negative means we spin clockwise. And if I go 6 pi over 6 plus another pi over 6, notice that I'll land in quadrant 2. And we know in quadrant 2, x values are negative, y values are positive. So I could have approached this from a totally different way, just by using the reference angle in quadrant 2 as being pi over 6, and noting that cosine was going to have a negative answer and sine was going to have a positive answer. Okay, but I took a different approach and used properties of sine and cosine being even and odd to do that. You still end up with the same answer. All right, so let's look at example C. So for example C, we have a situation where our radial coordinate and our angle are both negative. And so one of the things that I want you to note here is that we can convert this into a way that's going to be a little bit more beneficial for us to deal with. Okay, so I want you to note that we can take this and we could translate this way. Okay, now how am I able to do that? Well, let's look at what this looks like graphically and then figure it out. So if I was to plot this point here, and let's say this is negative 2, 0, then I would come out from the origin to this point here and then spin, sorry, I need to go in the other direction. And then spin this way 19 degrees, okay? So if I do that, notice that I am at an angle from a standard position standpoint that is in quadrant 2, okay? And so this angle here is basically 180 minus the 19 that I have here. And that's how I get the minus 161, okay? And notice that if I'm spinning from the positive x-axis in rotating in a counterclockwise manner, I'm assuming that my radial coordinate is now non-negative instead of negative. So I converted it this way just to make it a little bit more simple for us, since we're used to dealing with sine and cosine, where the radial component part of it is going to be positive and our angle is in standard position. So now that we have that, here we know that x is our cosine theta, which is just going to be 2 cosine of 161 degrees, and y is going to be our sine theta, which is 2 is equal to sine of 161 degrees. And so for here, we'll need to put this into our calculators and make sure that you are in degree mode when you do it. And what you should get here is a negative 1.891 for the x coordinate and a positive 0.651 for the y coordinate. And that's just me rounding to 3 decimal places. So of course, our answer here, and I'm going to recognize the fact that I'm giving an approximation here. It's just going to be this particular point. Okay, so for our next set of examples, we're going to switch gears here. And instead of taking polar coordinates and converting them into Cartesian or rectangular coordinates, we're going to go in the opposite direction. So we're going to take a Cartesian coordinate and we're going to translate it into or convert it into a polar coordinate. And when we do this, we're going to assume that our radial coordinate is going to be non-negative and that our angular coordinate is going to be in standard position and in radians. Okay, so we kind of put ourselves in this box here. So To do this, first we need to recall that we know that x is going to be r cosine theta. Y is going to be r sine theta. R itself is equal to the square root of x squared plus y squared. And finally, we know that that angle theta could be determined in several different ways, but our standard way of doing it is just using tangent. And we recognize that we're going to have to know what quadrant the angle is in to be able to use this equation properly. And we may have to use reference angles to be able to get there. Okay. All right. So first things first, let's go ahead and calculate what our radial coordinate is, since that's relatively straightforward. And we need that to be able to figure out what x and y are anyway. Well, not figure out what x and y are, but we need that to be able to find out our polar coordinate. So we're here. And so all I really need to do is just take whatever x and y are here. The x coordinate is 4 times square root of 3. The y coordinate is 4. So we're going to take these and square them. So for this first term, this is, since it's 4 times square root of 3, this would be like 4 squared, which is 16, times square root of 3 squared, which is just 3. Okay, so that's going to be basically 16 times 3 there. Okay. I'm going to write it like this. And then, of course, 4 squared is 16 again. And we could look at this like 48 plus 16, which is going to be 64. And of course, square root of 64 is 8. So we know what our radial coordinate is now. So the next thing we need to do is identify where our angle is. Now, note that our x and y coordinate are both positive. So since they're both positive here, notice that our angle is going to be in quadrant 1. Okay. And our x coordinate is 4 times square root of 3. Our y coordinate is 4. So if we use what we know about right triangles here, notice that if we have some angle and this side is a and this side is a times square root of 3, then we know that this is a 30, 60, 90 right triangle. The hypotenuse of this is 2a. And we know our angle, since it's opposite from the shortest side, that's going to be, since we have to do it in radians, this is going to be pi over 6. So we know our angle is pi over 6 just by the relationship of what we see with these sides of this right triangle that can be formed from the positive x-axis and the terminal side of the angle theta. Okay. Now there's other ways to do it. Like I could actually go and plug in r cosine theta, r sine theta into here and do all that. But I think this is the easiest way to go about it, leveraging what we know from geometry. Okay. So we know that our angle here is pi over 6. So now we got what we need. So this means our polar coordinate is just going to be 8, pi over 6. Or if you want, you could express it this way. Okay. All right, so let's look at example B. So example B, we're going to do a similar thing. We could calculate what r is first. We know that r is just going to be the x coordinate squared plus the y coordinate squared, and then we take the square root of that. So let's get this all together here. And so from here, again, a negative 4 squared is going to be a positive 16. And a square root of 2 squared is going to be a positive 2. And we'll do it again. So 4 squared is 16. And square root of 2 squared is 2. So we basically have 32 plus 32, which again is going to be 64, and square root of that is 8. So we know what our radial component is. Notice that for our Cartesian coordinates here, we have a negative x coordinate and a positive y coordinate. Okay. So since we have a negative x coordinate and a positive y coordinate, that tells us that our angle here is going to be in quadrant 2. Okay. And so in noting that, we can form this right triangle here. We can use a reference angle that I'm going to call alpha. And this is going to be 4 times square root of 2, 4 times square root of 2 here. Of course, we know that this 4 times square root of 2 down here on the bottom is negative, but I'm not going to write it like that. I'm just going to note that we know that the x coordinate is negative, the y coordinate is positive. So from here, if we look at this, we know that whenever we have a right triangle where the two legs are the same length, and we have, and I'm going to put angle alpha here just to be consistent with what I have. If I have an angle alpha here, then what we know is that this is a 45, 45, 90 right triangle. So alpha ends up being 45 degrees, or if we want to express that in radians, that is pi over 4. The hypotenuse here is going to be a times square root of 2. Okay. We don't really need to know that for this example, but we're going to need it for other stuff. So I'm going ahead and mention it now. And since our reference angle here is pi over 4, our actual angle, since it's in quadrant 2, is going to be pi minus pi over 4. So in other words, this is at pi here, and we have to go back pi over 4 or subtract pi over 4 units away from it. And here we end up getting, since this could be written as 4 pi over 4, 3 pi over 4. Okay. So our answer here will just simply be 8, 3 pi over 4. Or if you want, you could express it this way. All right, so that concludes our second example. So let's go ahead and do the third example here. And so for this one, notice, and I'm going to switch this one up a bit. Notice here that this point has a negative x coordinate and a negative y coordinate. So automatically that lets us know that we are in quadrant 3 here. Okay. And we can form right triangle here. Let's use a reference angle alpha. And I'm going to say that this is the actual angle theta that I want here. Okay. And so now that we have that, if I look at the sides here, I know that the x coordinate is 3, and I'm ignoring the negative here because I'm noting it down here. And I know that this is 3 root 3. And again, ignoring the negative because I'm notating that here in this point. So again, this is very much like this first example where we had the y coordinate being 4, x coordinate being 4 times square root of 3. This looks kind of similar to that. So we have a situation where you have the x coordinate here, y coordinate like that. This is your alpha. So we know that this is a 30, 60, 90 right triangle. In this case, since alpha is across from the, or opposite of the second largest side, we know that this is just going to be pi over 3 this time, okay? If our alpha was across from 3, like if this was alpha up here and we looked across there, then alpha would be pi over 6. But since it's across from the second largest side, it will be that. And we know that this is the second largest side because, of course, if this is 3, this is 3 times square root of 3, then this is going to be 3 times 2, which is 6. And again, that comes from the fact that if we know what A is, the hypotenuse is always 2 times A. Okay. And in this case, our A is 3. So 2 times 3 is going to give us 6. All right. So this lets us know what our angle is. And thus, to figure out what theta is, we're going to have pi plus alpha in this case. Because to get to theta, I have to rotate pi radians and then add another alpha radians to that. Okay. So this will be pi plus pi over 3, which will essentially be 4 pi over 3. So I started off this time with the actual angle. So now that we know what our angle is, we can now figure out what r is. And that's just square root of -3 squared plus -3 times square root of 3 squared. Okay, so that's 9 square root, -3 squared is 9 plus, and then since I have -3 times square root of 3, I have to square each of these factors. So -3 squared is 9, and square root of 3 squared is 3. And so this is just 9 plus 27 under the radical, which is 36 under the radical, and square root of that would be 6. So therefore, our final answer here would just be 6 comma 4 pi divided by 3. And again, you could express it this way if you wish. Okay, so we are done with our examples on converting polar coordinates into rectangular ones, as well as rectangular coordinates into polar ones. So this concludes the second video in this video series. The third video, what we'll do is kind of switch gears again, and instead of converting just polar coordinates into rectangular ones and vice versa, we're actually going to now look at polar equations and convert those into rectangular ones and vice versa. So hope to see you in that next video. Take care.